All right, let's take a look at example 10. So a Carnot cycle operating between 600 degrees C and 25 degrees C absorbs 1,000 kilojoules of heat from the high temperature reservoir. The work produced is used to power another Carnot cycle, which transfers 1,000 kilojoules of heat from 600 degrees C to a reservoir at higher temperature TH. Calculate the amount of work exchanged between the two cycles. Calculate the temperature TH, so that's for cycle 2, and calculate the amount of heat that's transferred to the reservoir at TH. So Carnot cycle is our reversible cycle. So I'll assume that you've read through the material and the text on Carnot cycles, and so I won't derive the relevant main results, but instead, write them down here. And so the main, results that we'll leverage from our Carnot cycle is first in defining the efficiency of our cycle. Right? So if I were to define my efficiency of my Carnot cycle, so just in general, right? So if you think about a Carnot cycle, we think about the steam engine and the Industrial Revolution. The goal is to convert heat to work. So when I think about defining an efficiency, the efficiency is desired output over required input. Desired output over required input. So what I'm trying to do, right, and say my steam engine is convert heat to work. So my desired output, right, is W, and my required input is going to be Q, okay, and here I'm going to write as QH because it's going to be heat delivered to my system from some hotter body reservoir. So I have some, body at a higher temperature, TH, that delivers heat to my system. I extract work, and then heat's exchanged with the lower temperature reservoir as well. So the efficiency of my Carnot cycle is equivalent to my desired output, which is the work, over required input, which is Q. So now W is going to be work done by my system on the surroundings, so I know that'll be negative. QH is going to be work added to my system, so it's going to be positive. Okay, so I add a negative sign here, right, just to make sure that it's positive. Okay, and you could go through and you could, derive, said relationships in the text, but, just think required output or desired output over required input. And for the Carnot cycle, we get the special equation that's equal to 1 minus TL, the temperature of my cool body reservoir, divided by TH, the temperature of my hot body reservoir. So TH, that hot body, which is supplying the required heat. Okay, cool. All right, so now let's draw a picture. Okay, now we have our main equation. Let's draw our picture and try and figure out what we have. So our first cycle is our Carnot cycle as we would typically think of it. So I have some hot body reservoir at some temperature TH. Let me call this TH1. Okay, that's going to deliver heat. Call it QH1. Okay, and then it's going to deliver heat to my system. And so here's my Carnot cycle as I'm depicting it here. Okay, and I'm going to extract some work from my cycle. Okay, so this W1 will correspond to the net work. So remember my Carnot cycle, if we picture it on our T versus S phase diagram, we have two isothermal processes in which we're exchanging heat with our reservoir, our hot body reservoir and our cool body reservoir. And then we have two isentropic steps. Each one of those steps, there's going to be some work exchange. Here we're looking at the net work exchange, right? Net work exchange between our system and surroundings. All right, so we'll have some work coming out, and then we'll also reject some heat, right, to my low temperature reservoir. Okay, cool. Now in this case, that work that we're extracting from our first cycle is the input to my second cycle, and my second cycle is going to do the opposite. It's going to take heat from the second low temperature reservoir. So it's going to extract heat, right, QL2, and then it's going to deliver heat to a second high temperature reservoir. Okay. So it's going to take work in, so it's going to take work as an input, and it's going to move heat from a low temperature reservoir to a high temperature reservoir. Cool. So let's go. And so, hey, this seems kind of like an air conditioner, right? In which we're rejecting heat outdoors. But let's see what we've got here. So now we're told that the first Carnot cycle is operating between 600 degrees C and 25 degrees C and absorbs 1,000 kilojoules of heat from the high temperature reservoir. So TH1 is 600 degrees C. TL1 is 25 degrees C. And we're told that the heat absorbed from the high temperature reservoir is 1,000 kilojoules. All right, that's 1,000 kilojoules. Then the work produced is used to power the second Carnot cycle, which transfers 1,000 kilojoules of heat from 600 degrees C to a reservoir at a higher temperature TH. Okay. So in the second cycle, when I think about this one, independently, TL2 is at 600 degrees C, which just so happens to be equal to the temperature of the hot reservoir. And so it's going to extract 1,000 kilojoules from TL2, and it's going to deliver it up to this high temperature reservoir. Okay. So that's going to be QH2, and that's going to be TH2. Okay. And I don't know what TH2 is. And do I know what QH2 is? I don't think so. Right? Because all we're told is the work is used to power another Carnot cycle, which transfers 1,000 kilojoules of heat from 600 degrees C to a reservoir at a temperature TH. So it's going to deliver 1,000 kilojoules of heat from our low temperature reservoir to our high temperature reservoir. Based on what I'm reading, I'm taking this to be QL2 is the 1,000 and not QH2. But it's not exactly. Oh, but then C, calculate the amount of heat that's transferred to the reservoir at TH. Yeah, so we've got our picture labeled right. All right, so let's see what we can do in terms of solving this. So let's start with our first cycle. Okay, so if I analyze cycle 1, okay, looking at it, I don't know what W1 is, and I don't know what QL1 is. Okay. So what I do know, though, is again I have my definition of my efficiency. So my Carnot efficiency, say for cycle 1, is going to be equal to, okay, my desired output would be negative, and I'll label it W1 here, divided by my required input, which is QH1. Okay, so I know W or QH1, I don't know what W1 is, and that's going to be equal to 1 minus temperature of my low body temperature reservoir, that's TL1, divided by TH1. I know TL1 and I know TH1. That's good, right? So one note, this is a ratio of temperatures, so I'm going to have to make sure I use Kelvin here. Okay, so if I look at this equation, right, I know TL1, I know TH1, so hence I know eta. I know QH1, I just don't know W1. So solving for W1, okay, take it one step at a time. Negative W1 then would be equal to QH1 times 1 minus TL1 divided by TH1. So W1 would be equal to negative QH1 times 1 minus TL1 divided by TH1. Okay. And just a quick sanity check. I know TH1 is going to be greater than TL1, so this ratio is less than 1. So this term in parentheses will be positive. Q's heat added to my system, so it'll be positive. So the negative, right, again ensures that W1 is negative. It's work delivered, work from my system performed on my work. My system's doing work. Work's performing system on the surroundings. So let me box that in. So let's add a new page and let's keep going. So I'll go to MATLAB momentarily and we can calculate that, but let's just take W1 being known. But then as I look at my second cycle, so my second cycle I need TH, and I also need QH, that heat that, well, yeah, so they want QH, the heat being rejected, along with TH2. Cool. All right, and just for completeness, if I want a QL1 here, okay, let me go ahead and let me just compute QL1, only because we'll apply the same principle here. Okay, and the basic premise is we're dealing with a cycle, and so remember the whole idea with the cycle is that we start and end at the same point. So when I think about my Carnot cycle on a T versus S phase diagram, all right, I start at point A. I have an isothermal heat exchange with my hot body. Then I have an isentropic step at constant entropy. Another isothermal step in which I exchange heat with my low temperature reservoir. Then another isentropic step in which I come back to my original state. So when I analyze my cycle, all right, okay, I'm starting and ending at the same point. So the significance of that is, the state of that system is fixed. So if I want to calculate the change in internal energy for that cycle, right, it's zero because I'm starting and ending at the same point. So the internal energy at my starting point and ending point is exactly the same. All right, delta U for my cycle is zero. Delta S for my cycle is zero. Delta H for my cycle is zero. Now Q and W are not zero because they're path dependent. All right, so when it comes to analyzing my cycle, all right, I would get the delta U1, so I write down my first law of balance, right, is equal to 0, and that's going to be equal to Q plus W. Okay, well here now, Q, okay, is meant to represent, heat exchange with both my hot and low, right? This is my net heat exchange. So this would correspond to, and so let me put a 1 on here, that correspond to QH1 plus QL1, and then W1's my net work exchange. So that's a plus W1. Okay, so if I wanted to solve for QL1 is just equal to then negative W1 minus QH1. So QL1 is just negative W1 minus QH1. Okay, so if I go up here, okay, so if I go to cycle 2 and I think about, I have problems B and C to solve, okay, let me start with C just because it's the same principle, right, and then we can get our temperature from our efficiency. But if I know W1, okay, which I just calculated here, right, so it's known. So if I know W1 and I know QL2, then I can get QH2 just from a balance. Okay, so again, the whole idea is so now W2, the net work of cycle 2 is just equal to W1, right? So it's taking work in, and the whole premise is for my cycle, I'm starting and ending at the same point. So I would have that delta U2 is equal to 0, and that's equal to Q2 plus W2. Okay, where Q2 is going to correspond to QH2 plus QL2. Okay, now W2, okay, I just need to make sure I get the sign right. Okay, and when I calculate the sign of all my terms, right, we can check to make sure it's right. W1 is written is work, so W1 is going to be negative, right, because my system 1, right, my first Carnot cycle is going to be performing work. Right, so W1 is negative. Now in the context of cycle 2, right, cycle 1 is doing work, all right, that cycle 2 is receiving, right? So this could be work done on cycle 2. So to get my sign convention right, what's key is that, okay, let me just write it here, is that W2 is going to be equal to negative W1. Because cycle 1 is doing work, right? It's doing work on cycle 2. So it's going to be a work input to cycle 2. So this will be a minus W1. Okay, so solving then, if I want QH2 in this case is going to be equal to W1 minus QL2. Okay, so it'll be W1 minus QL2, where QL2 we were given. All right, now a check of, sanity check as we go through this. Okay, so if I come back up to problem 1, okay, so we said W1 is going to be negative, right? W1 is going to be negative. Now also so W1 is going to be negative, and so it's going to be equal to negative QH1 times 1 minus TL1 divided by TH1. So this term is less than 1. So W1 then is going to be negative and less in magnitude than QH1. Okay, so the fact that all three of these have to sum to 0, okay, so QL1, well, let's see, so W1's less than QH, which is that original 1,000 kilojoules. So this should be less than QL2 then, since QL2 is also 1,000 kilojoules. So QH2 is negative, which should work out because I'm rejecting heat. So again, it just works out because QH1 is 1,000 and QL2 here is 1,000. And so since W1 plus QL1 have to sum to give you QH1, okay, W1 is going to be less than QH1. Okay, now QL2 just so happens to be equal to QH1. So, the fact that this becomes negative W1 is W2 is negative W1, I get that this would be negative, right? Because this is 1,000. This, which would be negative W1, is going to be less than, its absolute value is less than 1,000, so QH2 has to be negative. Okay, so also check out. Then the last thing they want, and so I've got QL1, I've got QH2 then, they want TH2. Okay, how I'm going to get TH2 is you could calculate TH2 via my efficiency again. Okay, so now the efficiency, is so my Carnot efficiency. Okay, so when I look at it this way, right, it's still the same cycle, right? It's just, we're doing the opposite thing. Okay, and so I'm still going to write my Carnot efficiency the same way. So it's going to be, this negative W1 over QH. So it'd be negative W2, which would be equal to positive W1 over QH2 is equal to 1 minus TL1 over TH1. Okay. Did I get that right? Well, let's see. So I've got QH2. So then Carnot efficiency is going to be equal to yeah, so let's so yeah. So let's write this down. So let's write my Carnot efficiency is going to be equal to, so I'll write it as negative W2 over QH2, okay, where W2 is equal to negative W1. So this is W1 divided by QH2. Okay. Now W1's negative, QH2 is also negative, so that's good. And that's going to be equal to 1 minus temperature of my, so TL2 divided by TH2. Okay. All right. So if I wanted to solve for TH2 then, so I know W1, I know QH2, so let's solve. So I can write this as TL2 over TH2 is equal to 1 minus W1 over QH2. So therefore, TH2 is equal to TL2 divided by 1 minus W1 over QH2. Now let's go over to MATLAB, let's compute, and let's see if the answer makes sense.
Okay, let's head over to MATLAB now and perform our calculation. So I'm going to start by creating a new script, and before I forget, I'm going to save it as chapter 410 for chapter 4, problem 10. And I'm going to start by just assigning two variables the quantities that were given in the problem that we need to perform our calculations. So TH1 was 600 degrees C, and I'm going to go ahead and add to it 273.15 to convert it from Celsius to Kelvin. Since when I perform my calculation of my Carnot efficiency, I have a ratio of temperatures. I need to make sure that I'm using absolute temperature units, so either Kelvin or Rankine. So TH1 was 600, TL1 was 25, but again, adding to it 273.15 to get that in Kelvin. And then we also have QH1 is 1000, and that's 1000 kilojoules. So QH1, and so that's going to be positive because it's heat added to my system, so that's a positive 1000 kilojoules. It's extensive heat, but that's okay when we perform our calculation of our cycles. Right, what's key is within our cycle, right, it's a closed system, no mass is being lost to my surroundings, so mass will be constant within that cycle. And so mass would say cancel out of that expression. Right, so since mass is constant, I can use intensive or extensive quantities for my heat and work for that analysis. Okay, so that's QH1, and then we also have TL2 is 600. Okay, adding to it my 273.15 to get it in Kelvin. Okay, and then finally I'll add my QL2. That was also 1000 kilojoules. Okay, just like it doesn't matter if Q's intensive or extensive, right? The values of kilojoules are fine, right, as long as I'm consistent throughout that, first law of balance on my cycle. So if QH1's in, kilojoules, well then QL1 will be in kilojoules, and W1, right, will also be in kilojoules. We'll go ahead and perform our calculations, right? So again, just to be clear with units, so this is a ratio of our absolute temperatures, so this is dimensionless. So this term in parentheses is dimensionless. So W1 is going to have the same units as QH1, which will be kilojoules, right? So it's just a matter of, keeping track and being consistent. Okay. So W1 is going to be equal to negative QH1. Okay. So QH1 is positive, so this is going to be negative. Okay, which again makes sense since it's work done by our system on our surroundings, or in this case, work done on system 2. So it'll be 1 minus TL1 divided by TH1. Okay, so that's W1. Okay, then if I want to get QL1, we have that QL1 was equal to negative W1 minus QH1. Okay, and then finally, not finally, so QH2 was equal to W1 minus QL2. Okay. Then finally, TH2 is going to be equal to TL2 divided by 1 minus W1 divided by QH2. Okay, 1 minus W1 divided by QH2, so TL2 divided by that. Okay, so running. Okay, so let's see. So I've got an error, TH1. So here, so TL2. It's because TL2 is 600, and I call the TL1 here. So that's supposed to be TL2. Okay, so then running, right, it works. Okay. And we get that W1, okay, is a negative 658.5352. That'd be kilojoules. So it's negative because it's work done by System 1 on our surroundings, which then becomes a work input for System 2. So W2 would be a positive 658.5352 kilojoules. QL1, okay, so W1 plus QL1 was equal to QH1, which was that 1000 kilojoules input. Okay, so this is the heat removed, and that's the work done by my system. QH2, okay, and TH2. Okay, so looking at what that is, so QL2, this is the heat removed from my cold body, okay, which we're able to do because we're adding or performing work on our system. Okay, is equal to that heat rejected to my hot body. Okay, and that's what's going to be QH2, which somehow there was erased. So the heat removed from System 2 and heat rejected to that hot body would be so it's a negative because it's heat rejected, but it's 1.6585 times 10 to the 3. So that's 1,658.5 kilojoules. And the temperature of our hot body is 1.4482 times 10 to the 3. So that's 1,448.2 degrees Kelvin, right? So this would be a 1,448.2, okay, and that's going to be Kelvin. And then if I want to get that into degrees C, okay, let me just, so TH2 in degrees C would be TH2 minus 273.15. Just so we're all on the same page, so that's a 1,175 degrees C. Okay, so the temperature of my second hot body, so TH2 is 1,175 degrees C. Okay, so I calculate the value in Kelvin because as I perform the calculation, I'm using absolute temperature units, and then I'm converting to degrees C just because all of these other temperatures are in degrees C. Okay, and so all the values are given here in the MATLAB code. So hopefully that helps. And if you have any questions, by all means, just let me know. But we checked the problem all along as we were working through it to perform our sanity check, and so all should be good. Okay, we'll see you in the next problem.